Welcome to the Digital Amateur Television Experimenters Night. This is VK7OTC, the club station of the Radio and Electronics Association of Southern Tasmania. Amateur radio is a worldwide hobby that has many different aspects. Digital television is just one of the many modes and areas that are covered. Maybe you're interested in becoming involved in the DATV Experimenters Nights. You realise that you do not have to be a radio amateur or need any ATV equipment to participate anywhere in the world. Also participate in the night by coming up to the Queen's Domain club rooms. Yes, right on top of the Queen's Domain in the heritage-listed Coast Wireless Station. You never know, we might get you in front of the camera or behind doing one of the many roles during the night. We get underway with our program on a Wednesday night from 7:30 p.m. local time. We'll see you soon. This is VK7OTC.
Okay, that was a rather severe transition, wasn't it? This is VK7OTC, the club station of the Radio and Electronics Association of Southern Tasmania with our DATV Experimenters Night. And I have regular contributor Rex VK7MO.
Thank you, Justin.
Evening, how are you going?
Good.
Excellent. Now, Rex is in the studio because there is some very interesting research you've been doing. So tell us a bit about that.
Okay, we'll just go to a slide.
We will get there.
Yeah.
There we go.
Now, some of you will have noticed that, in fact, it was on a broadcast for VK7 on Sunday that a new version of WSJT had come out. Mainly it fixed some bugs and defects.
Yep.
But it also mentioned that there was an enhanced decoder for aircraft scatter. And that was something that I had been working on with a friend, Roger W3SZ, for the last few months. And a few weeks ago we got to the point where we submitted it to Joe Taylor.
Cool.
Roger actually wrote the coding, and Joe included the code in this latest release.
Now that's pretty impressive that Roger actually wrote the code.
Yes.
We'll just go back. What's Roger's background?
Roger is a cardiologist.
Okay.
So but he's amazingly good at writing code and getting inside WSJT and knowing how to do things.
Wow, okay.
And he's also good at writing code to do things like simulate Doppler shift on WSJT signals so that we can test things.
Right.
So a lot of this is as a result of what Roger has contributed.
Okay.
My bit has mainly been testing and asking silly questions, and he then reacts to my silly questions. We sort of run into each other almost by accident because he was asking David VK3HSZ and I had written some papers on aircraft scatter, and they'd sort of fallen off the web, and he sent me an email asking me, he was referring to them, and could he, in his own website, and he wanted to sort this out, and I said, oh, just by the way, this new Q65 works pretty well, and here's an example, and we started working with each other, and we've had a lot of fun together.
Well, there you go.
And I think our skills have complemented each other very well.
Okay.
So we'll just now go through the developments of Q65 for aircraft scatter. This is the test path that I've been using with VK3WE, who's in Bensdale.
Just hold that thought, Rex. I'll just
What's happening? Something's not happening?
Something's not happening. We've got that's solid, and I'm not sure what's going on here. Okay, let me just try something else.
It's not going out.
Apologies to our listeners.
Coming out on the monitor out there.
No, but the images are not coming out, are they?
That's there we are.
What, are you seeing a map of Tasmania?
Oh no.
No.
No. That's what I mean. It's where I'm just resetting. Apologies about this, Rex. I'm in a little bit of a loss. We've actually got let's just try that again. Beautiful. Okay. Now. Yes.
Okay.
It was a video mixer problem, just for those. So bear with us, people.
All right. This is the test path that I've been using from Hobart up to VK3 Whiskey Echo in Bensdale in Victoria.
That's Rhett.
Rhett?
Yes.
That's right.
Okay, cool.
And he runs 10 watts to a 60 centimetre dish.
Okay.
And I've been running 90 watts to a 1.2 metre dish.
Okay.
And we've been testing aircraft scatter, and typically with the first version of WSJT, it was with first version of Q65, it was working pretty well, providing the aircraft didn't cross at a very sharp angle. So this is probably about 10 or 15 degrees that the aircraft is crossing in this case.
Okay.
And that's the Hobart to Sydney aircraft, which nicely crosses the path some of the time.
Yeah. So it goes up and basically turns a corner and then goes off to Sydney.
Sydney. Unfortunately, sometimes they just fly straight to Sydney and don't cross the path.
Oh, okay. So they take off from here and go across here.
And that's
Yeah,
right.
okay.
But when they do, that works pretty well. And the next slide.
So that's 100, 150 and 200 nautical miles.
Yes,
Those-
the distance from me to Rhett is 560 kilometres.
Right. Okay. Okay. Cool.
And this is an example of the sort of signals we were getting with the original version 2.4 of Q65.
Okay.
You can see the aircraft. The Q65 has a sync tone and then messages to the right, and you can see the sync tone is moving at an angle.
Yep.
Which is the Doppler shift.
So that's the 3 hertz per second.
That's at 3 hertz per second with this aircraft.
Okay.
And that's decoding pretty well, which was a bit of a surprise because 3 hertz per second over a 12, when you're using 15-second periods, it actually transmits for about 12.6 seconds.
Okay.
And that's about 36 hertz over a transmission.
Okay.
And the tone spacing's only 26 hertz.
Okay.
So
So it's actually moved further than what the tone spacing is,
yes,
and it's still decoding.
yes. So that was a bit of a surprise.
Okay.
We've got some thoughts which I'll mention later.
Okay.
You also notice that the signal every second period is much stronger. That's when I'm transmitting to Rhett
Yes.
with my 90 watts against his 10 watts.
Yep.
When I'm actually transmitting 90 watts, you can actually see a constant signal as well, which is troposcatter.
Oh, sorry.
If you
I'm just getting the cursor up. Yep.
if you move to the left of the and down a bit, see there?
Oh, there.
Yeah.
Yeah.
So he actually could receive my troposcatter as well.
Yeah, okay,
But I
okay.
couldn't receive the troposcatter from his 10 watts.
Okay.
You'll notice that the even on my 90 watts, there's sort of signal that's quite strong in parts and weakens off,
Bit variable.
even within just a 15-second period.
Yep.
And the next slide gives you a clue. Oh, first of all, before we go,
Okay.
you'll see this is decoding quite well with signal levels sort of plus 3 dB.
Minus
plus,
3.
There's a plus 8 right down to minus
Oh.
19.
Oh my god. Yeah.
So a lot of variability.
Okay.
And the next slide gives us a clue as to what's happening. 10 gigs aircraft scatter comes in bursts, and with a very low Doppler shift, the bursts are fairly spread out. These are 15 seconds long,
Okay.
or 15 seconds, so each of these vertical segments are 1 second, and there's
So these lines.
yes, are 1 second apart.
Okay.
And you can see the signals varying quite dramatically because the lines in the vertical dimension are 5 dB steps, so
Okay.
this is more than 25 dB of
A variation.
variation.
Yeah. Okay.
Then when the Doppler shift is much faster, the QSB is very rapid,
All over the place.
jumping up and down. And
Now that's over a shorter path. What's
the reason for that is I went up north to try and simulate a larger Doppler shift.
Yeah. Okay.
And went to Table Cape.
Okay.
And the crossing angle of the path across to Rhett from Table Cape wasn't right angles, but it was
Okay.
probably 50, 60 degrees.
Yeah.
So
Okay. Okay.
So
hence the greatest Doppler shift.
greater Doppler shift.
Yep.
But the path was actually a lot shorter, and in fact there was troposcatter there all the time. But this is we can see the signal dominated from
From the aircraft scatter.
For the aircraft scatter.
Okay. Cool.
So you've got a decoder signal if it's crossing with a large amount of Doppler that has very rapid QSB.
Yep.
And surprisingly, Q65 is really good at
Dealing with it.
Dealing with this.
Wow. Okay.
So we go to the next slide. Now, in this case, what we're dealing with is an aircraft that's flying from Auckland to Perth,
Oh, okay.
and just occasionally the Auckland to Perth aircraft flies down the middle of Bass Strait
Oh, cool.
and is useful for us, but it has massive Doppler shift, like 13 hertz per second.
And you only get 3 cycles.
That's right, because it gets past the path very quickly.
Okay, yes.
Not only do you only get 3 cycles, but you don't even really get 3. You get sort of a short bit at the start and a
nothing
short
at the end.
But nevertheless,
Okay.
even though it's on a short bit at the start, you'll see it's decoding perfectly.
But it's interesting. It's the same on both ends, and then it's huge in the
Oh,
middle.
the reason is Rhett's transmitting at
Okay, yeah. Lower power, smaller dish.
and he's just transmitting constant message.
Yeah. Okay.
And I'm transmitting back to him.
Okay. Wow. Okay.
Now, how we got to work, originally version 2.4 worked up to about 4 hertz per second shift.
Okay.
And we sent Joe Taylor some files. Well, first of all, Joe Taylor came out and said that he was producing a version of Q65 which would compensate for frequency shift, because he found a lot of people who were used to the AFC system on JT65 didn't like, or didn't have stable enough rigs on.
Okay.
And so I went back to Joe and said, look, if you're going to compensate for frequency shift, can you make it work much over a wider shift to cope with Doppler? And he came back about 24 hours later and he decoded these files that I sent him, which wouldn't decode before.
Okay.
So this was a very dramatic advance
Wow.
in version 2.5.
Okay.
And really decodes quite well. So then we looked at whether we could improve the decoding by applying a different decoder or the Doppler shift to one of the other decoders that Joe was using.
Okay.
And that was what became ultimately version 2.5.1.
Okay.
If we go to the next slide, this is the enhanced decoder, and you can see the signals are very weak. This is actually a test that Roger did between W1FKF. This is over about a 500 kilometre path.
Okay.
They're in the northeast of the USA, so they're not short of aeroplanes. The whole of Roger's sort of inland in Pennsylvania up to New Hampshire, and all these aircraft flying into New York and
the eastern seaboard
are flying across the path, and you can see these are fairly weak aircraft signals, and our new decoder gives it what's called a Q5 at the end of the line. That's only for the purpose of identifying which decoder is being used.
Yeah, okay.
And you'll notice that on this group of messages, which were selected all to have more than 7 hertz per second of Doppler shift, which is where this decoder works, that it added 3 more decodes by using the Q5 decoder.
Okay.
If you look at the actual lines where the Q5s are, most of them You can hardly see
can't see anything.
any aircraft whatsoever.
Correct.
And so, and it is decoding off the aircraft.
Okay.
Because we can measure the Doppler shift.
Yep. Yeah.
So the
Great improvement.
it's a significant improvement.
Okay.
So we'll go to the next slide. Now, compared to iSCAT, which we used to use in the past, Q65's got a lot of forward error correction, and so it doesn't make mistakes. All of the decodes...
Less mistakes.
Well, we have never seen a
false decode.
A false decode
Okay.
in on-air testing.
Okay. Fantastic.
So, but if you look at an iSCAT signal...
It's all over the place, yeah.
Now, because iSCAT actually decodes every 2 seconds,
Yep.
you get enough so that by eye you can say, yeah, there's a fair chance that that's VK3WE
Yep.
and VK7MO
Yep.
and the
Okay.
report's an OO
Yep.
report. But it is... There are a lot of false decodes, and when you're out and you just get a very short burst, you often get a false decode and you just get a bit annoyed because you know it's not the right signal.
Yeah.
So it's a big advantage over that.
iSCAT's also used for meteor scatter, isn't it? Meteor scatter?
It
No.
was originally designed for 6 metre meteor scatter, but the new MSK 441's overtaken it.
Yep. Okay.
And Joe's been pretty keen to get rid of iSCAT, so a couple of years ago he said to me, do we still need iSCAT? And I said, well, it is useful for aircraft scatter.
Not anymore.
Not anymore. So,
Okay.
next slide. Now what Roger did is he simulated various Doppler shifts, and you can see at the top of this table there are Doppler shifts of 0, 2, 4, 5, 10, 15 and 20 hertz per second.
Yep.
And we tried all various modes in this simulation to see how they compared.
Okay.
And you will see that I've coloured in green the original version of 2.4,
Okay.
yellow the 2.5 that Joe produced,
Yep.
and 2.51, which is the new version, which has just come out. And when the Doppler shift is quite large, there's significant benefits with the new version. You can see it's working at sort of minus 21 in the B mode compared to sort of the original version just not working at all.
Yeah.
iSCAT was working, but iSCAT's working at sort of minus 11, minus 10, and we're getting down to minus 21s. In fact, at 20 hertz per second, iSCAT's minus 9, so there's 12 dB
Improvement.
improvement.
Yep.
Now we looked at some other modes that we have. Roger in particular has been using JT9 for aircraft scatter, and with very wide Doppler shifts, it's also dropping off.
Yep.
And so we're still picking up the sort of 12 dB improvement.
Yep.
We looked at MSK 441, which works, but it doesn't have the sensitivity. It drops off.
Yep.
The VK7OTC's taken away the last number, but I think it's
minus 6, I think.
minus 6. So while my MSK works, it's way down on, and we tried FT8 just for fun, and interestingly enough, FT8, if you've got no Doppler shift,
It's great.
it's great. Not quite as sensitive as Q65 with no Doppler shift.
Yep.
But
But as soon as you get Doppler shift,
if
forget it.
any sort of Doppler shift or frequency stability problems, it falls away completely.
Okay.
we'll go into the
Fascinating.
next slide.
Absolutely fascinating.
So our conclusions are that both from our on-air tests and the simulations that we gain an advantage of somewhere between 5 and 12 dB, depending on the amount of Doppler shift.
Yep.
And in comparison to iSCAT, there is the forward error correction. It's virtually immune to false decodes,
Okay.
which is an advantage.
Yep.
So you can actually conclude that Joe can not be concerned about deleting iSCAT
yes.
from the
Huge improvement.
from the various modes that are available.
Okay.
And the acknowledgements, firstly to Roger, who did all the decoding of the enhanced decoder, Joe Taylor, Bill Somerville, Steve Frankie and Nico Palermo, who jointly produced 9-inch Q65, and in particular for that group for providing the new drift compensation feature,
Okay.
which in 2.51 implements Roger's code.
Okay.
And Rhett Donnan and VK3WE and Don Twomby, who was Roger's QSO partner,
Okay.
who did the tests.
Fantastic.
Okay, that's all.
That is excellent. Rex, what I will do, I'll just quickly go back to, and hello from Richard, who is greetings to all from Burnie. So he's up in Burnie tonight. So hello, Richard. I hope you have lots of questions for Rex that you can send through on the chat channel. And just a reminder, if you've got if you're on the chat channel, and there's a few people on there, please come back to us and let us know that you're there, and let us know any questions that you may have about the presentation tonight. So please come through. Also monitoring repeater 2. So if you've got a question on repeater 2, please have a shoot it through. Just got back, so we'll need to watch the replay. Oh, come on, Richard. Pay attention. So that's fantastic, Rex. Just the frequency shift feature.
Yes.
So they've made it so that it can deal with much greater shifts in frequency.
Yes. Providing they're linear.
Oh, okay. Right.
Which doesn't seem to matter with aircraft unless the aircraft changes course just at the time
That they're doing the decode, which is pretty unlikely.
Yes. It's. I think it can be a problem with its original purpose, which was to compensate for drifting rigs, because rigs tend to have a sort of exponential drift that if they're drifting because of heating and you go to receive
and it's on the edge of the pass band or something like that.
Well, it's not so much that, it's that you can't you can compensate. You don't have a linear drift, you have an exponential drift.
Yeah, okay. That was my question.
Yeah.
Can it deal with drift?
Now, JT65 did have a 3-point curve drift.
Okay.
And this only is linear drift. I think the reality is anybody who's serious about using these modes should be properly GPS locked.
Correct.
But you can't GPS lock the Doppler shift that an aircraft is doing.
Yeah, that'd be interesting, wouldn't it?
Yeah.
Constant frequency off the aircraft? No,
well,
mode?
It's some people have suggested that you could use the APRS system to detect the exact position of the aircraft and calculate the Doppler shift and
compensate for it.
Compensate for it. However, this method
Well,
the advantage of this method is it doesn't matter which aircraft's involved, and if you're on a path with lots of different aircraft, how are you going to pick the one that's
that you're actually scattering a signal off?
Yes.
And we do that in satellite communication. We predict the Doppler shift on it and compensate accordingly. So
yeah, it's not out of the question, but it's pretty difficult to do with aircraft.
Well and truly. Okay. Oh no, well that's excellent. Thank you, Rex, and congratulations on contributing yet another bunch of information towards the development of WSJT-X. So that's pretty impressive. So and linking up and networking with, by the sounds of it, exactly the right person.
Oh, we both seem to work amazingly well together.
Fantastic.
Yeah.
So and also for his medical advice as well.
Oh yes, he's been helping me understand some family problems.
Some family issues, yes. So good stuff. A bit of consulting on the side, yes.
Yes.
That is fantastic. Now, by all means, stick around, Rex, because we're going to do the second part of our talk on resonance, which and it's all about, hopefully, things which are a little bit more relevant to the amateur, because we're going into RF resonance. With just a bit of a recap. The reason I went down this path was I have an antenna on a pole outside that, when the wind's right, from the right direction and the right wind speed, it starts to resonate. It starts to audibly resonate at an audio frequency. Which of course I find fascinating, but the rest of the family in the middle of the night don't. So, that's what got me on this path, and we had Chladni plates that we were vibrating and getting patterns on and all sorts of stuff. So just a reminder, what is resonance? And it is very relevant to any form of resonance. So the actual description of resonance is increased amplitude where the frequency of a periodically applied force, which in the case of my antenna is the wind, is close to or equal to the natural frequency of that system. So the pipe, what it's connected to, the antenna, the elements on the antenna, etc., all contribute to making that system vibrate with the right amount of energy, the right amount of wind, and cause it to oscillate. And that oscillation is at a much greater amplitude, which is why you know that's the resonant frequency of that particular system. So when we apply it to RF, and what I'm going to do is use a little, this is actually a little antenna tuning unit that I made for an end-fed antenna, but I looked at it and I went, well, that's a variable capacitor, and that's an inductor that I wound, and they're in parallel, and I thought, well, there's a resonant circuit. So instead of actually making one up, here's one I prepared earlier. So what we are actually going to do here, and I'm going to try and do this with a couple of different pieces of test equipment. The very first one is a grid, well, it's probably a gate dip oscillator, because I suspect there is a FET in here, not a valve. But originally they were what we called grid dip oscillators, and all this is an oscillator that enables you to tune that oscillator, and there's a whole lot of little frequency scales on here that are associated with, this has got a little A on it, and the frequency is 0.7 to 1.6 megahertz. There's a little coil, and that plugs in and forms the part of the oscillator circuit. There is a variable tuning capacitor, which is calibrated. There's a little scale on here with a frequency on it, and then there is a sensitivity meter. Now there's a couple of different modes that you can use grid dip oscillators in, which is, one is it is an oscillator that is oscillating, and basically because this coil is out in the air, you can put this next to a component In this case, I'm going to be putting it next to the inductor here in the middle, and the energy that this oscillator creates is basically induced into that coil, and it literally, if you hold that up, Rex, so that we can see it on the screen, all I'm going to be doing is basically putting the coil in the middle of that toroid, and we'll show this on the screen, and then we're going to be looking at, there's a little meter on here that enables us, when the resonance of this oscillator equals the resonance of that circuit, that LC circuit, you get a little dip on the meter, and it indicates, and what you can then do is read off on this scale the frequency, and that's the frequency, the resonant frequency of this LC circuit, through the reading off the actual frequency on here. So what I'm going to do is we'll try and set up on the close-up camera here, and then what I'm actually going to do after that is do a slightly different way of representing this. So if we go to there and we zoom out here on our, thanks Rex, and we go to, so here's our variable capacitor. We can change the tuning of the resonant circuit, which is very handy, and here's our inductor. Now what I'm going to do is put the coil of the, now let's move this over a little bit, can we see everything? Now I'm just going to switch this on, and you'll notice the meter, I've got a bit of a sensitivity level pot here, so I'll stick that in about the middle, and this is 0.7 to 1.6 megs. So let's see with the variable capacitor all the way in whether we can find where we get a bit of a dip on the meter. Now. And it's pretty sharp, I can tell you now. Okay. Let's go up in frequency a little bit. 1.5 to 3.6. So let's see whether we can get a bit of a dip. Here we go. Oh, we're not getting a dip at all. So what are we at? We're on a B, so we're at about 3 megahertz. Let's see, let's try it a slightly different way, a bit more amplitude, and see whether we can, oh, there we go. So if you can just see the meter there, just kicking. And what I can do is then read off on here, it's B scale, it's about 3 megs where I am there. So if we go down, we'll go down slightly less. We'll see whether we can get the meter to dip at one end and the other end. Oh. Oh, there we go. That's a bit more of a pronounced dip. And what we're at 1.6 megs. So if we go all the way down, let's see if we can go down even further. Oh no. So it's about, there we go, just a little bit out of the, is about 1.5 megs. So it's about 1.5 or 1.4 all the way up to, if we go to the other end of the spectrum and then we go up in frequency, let's go to 3 and see where the variable capacitor is. Oh, there we go. So we're about halfway. So we actually have to go up even further in frequency. So we go to C, which is 3 megs to 7.4 megs. So let's put 3 to 7.4 megs in. Now that's scale number C. So let's go to say 5 megs. See whether we can get a bit of a dip happening on the meter. Oh, there we go. Just moving a little bit. Now, that's almost at the end of the stop here. So what we're talking about is about a 1.4. So what this variable capacitor gives us is a range in resonance of 1.4 megs to about 5 megs here. Probably a little bit more, maybe 5.5 megs. Let's go all the way to the end and see whether we can't get a bit of a dip. Oh, there we go, and that's about 6 megs. So the variable capacitor gives us this resonant circuit of a capacitor and an inductor, and what's happening here is the energy is being introduced through this coil on the Gate Dip Oscillator into this circuit, and both of these components store energy in different ways, and the energy is going backwards and forwards between those components at that resonant frequency. So that's about 1.4 to 6 megs. That's what we call a grid dip or a gate dip oscillator. Now another way of measuring this, which is slightly more up to date, is, and you've seen this on this program before, Nano-VNA. So you can use a Nano-VNA to do exactly the same thing. Now just bear with me whilst I set up. So the display trace, only want one trace. I want the format to be real. I want the scale, the stimulus, so this is the frequency. So let's start. We know that we're at about 1.4, so if we go from 500 kilohertz to, let's go to 10, or what was it, 6 megs, so let's go to 8 megs. So this scale now is from 500 kilohertz to 8 megs. Now what I've got on here is a few little turns on here with the B and C connector, and this is just more out of ease of coupling. So what you're seeing there, and we'll zoom in here, what you're seeing here is, now we've got those plates on the capacitor all the way out. So to check out where this peak is, let's move our tracer all the way up to where the peak is, and it's 5.85 megahertz. Now let's turn the variable capacitor all the way into, so they're all both meshed, and we can go all the way back to this other peak. Oh, hang on, sorry, that's me. Let it just stabilise, because I'm right next to the variable capacitor and a few other things, so there's lots of coupling going on here. Now at the low end where there's that little peak, and you'll notice the peak is really sharp down low, but it's really wide up the other end. So that says to me that probably the Q of this circuit's not that good. But this is measuring off. If you read that frequency, the minimum frequency is 1.25 megahertz. So that's just another way of saying the range of that resonant circuit of hang on, let me zoom out a bit, is confirming what we saw on the grid dip oscillator. So that's another use for a Nano-VNA. It's a bit off the shelf use for a Nano-VNA. It's but it actually shows what you can use a Nano-VNA for. So, any input, Rex? Any comments? Any?
No, I think that's the first time I've seen a Nano VNA used in that way, and I think that's very useful.
Well, I was using the grid dip oscillator to make sure that everything worked last night, and I suddenly thought, hang on, I've got basically a spectrum analyzer that enables me to sweep a spectrum analyzer with sort of a built-in tracking generator, sort of, and I went, well, I can actually sweep this, and I'm not quite sure what you'll be seeing when you sweep it, but with it set to a real, which is the particular setting in here that you can set it to, it actually shows you a peak that moves as you move the resonant circuit. So I went, okay,
Yeah.
that works. And can I just say the Nano-VNA is actually a whole lot cheaper than a grid dip oscillator. so there are certain advantages to
How much?
Well, this is around about $100 once it's landed here.
Yeah.
Versus a grid dip oscillator these days, for something like this, if you can even get one, you're probably talking about $150 to $200 at least, and that's hopefully you get all of the coils that go with it, etc., etc. There are some very impressive grid dip oscillators actually around that have a frequency display, a digital frequency display on them, and you basically dial in the frequency that you actually want to use. So there are some pretty impressive grid dip oscillators around. You can also use this as a bit of a field strength meter. And also, obviously, as a bit of a signal injector, there is a little probe in here that enables you to either search for a particular frequency or inject a particular frequency, depending on the mode that you're in. There's an oscillator versus a modulator type arrangement. So you can do it as a signal tracer or a signal injector as well. So that doesn't always come with a grid dip oscillator, but anyway. The other thing that comes on here is there's a little another socket on the front of here which is for a crystal. You can plug a crystal in and then find out roughly what the frequency is on here, or roughly what other frequencies the crystal will actually oscillate at. So the overtones of the crystal. Which is that can be a pretty handy little thing. How far can I push this crystal? You can at least get a bit of an idea about with your gate dip oscillator. I should call it a gate dip oscillator. So now I just wanted to show this is This is Ian Ridpath, and I've talked about Ian Ridpath. When he wrote this, he was ZL1BCG. This is the book that I learnt amateur radio from. Now, Ian Ridpath, it's funny, you know, I put his name in something somewhere, and I got this email out of the blue from an Ian Ridpath in Canada, who was ZL1BCG. So the internet's a wonderful thing when these sort of things happen. And he said, it's fantastic to hear that you used one of my books. Now, these books were available at Dick Smith Electronics. They are in a notebook, in a lab notebook format, so it's all handwritten. But this was what I learnt to do my my advanced theory, and it's a great little book that enables you to. It was actually made for New Zealand amateurs. However, it was very relevant to Australian theory as well. What you got here, and this is actually this was the formula that I wanted to show, and the fact that there is a little PO flag next to it means that it's a post office requirement to know this formula.
Right.
And this formula is to find the resonant frequency of an inductor and a capacitor parallel circuit is 1 over 2 pi the square root of the inductor and the capacitor in farads, henries and hertz. So that is a requirement of the current syllabus. You have to know that formula. And you actually
in
have
Australia?
to, yes, and you have to actually calculate. You're given the L and the C, and you need to calculate the frequency. So, it is that's a critical formula for resonance to find out the resonance of that circuit. So I just wanted to show that, and that's Ian Ridpath's amateur radio electronic study guide. You do come across these every so often in second-hand shops, and can I just say they are excellent because they are no longer in print. But if you find a copy, definitely grab it because it is it's a fantastic learning resource. So this is the A5 version. It also the version that I learned going to and from work on the train in Adelaide was the A4 version, which was the big version of this, and this is the 3rd edition. So yeah. Anyway, that's and there is a whole section on resonance because in the syllabus you actually need to know what resonance is and how to calculate it for particular circuits. So in the resonant in a resonant circuit, you've got this special condition where once those components are at resonance, what you magically find is at resonance there is no inductive or capacitive reactance in that circuit. So Ohm's law applies at resonance. So the impedance equals the resistance. So it is only the components in that circuit that so the inherent resistance in those components are the things that you use to calculate what the overall resistance of that circuit is at resonance, because at resonance there's no inductive capacitance, no inductive reactance and no capacitive reactance. As you go out of obviously out of resonance, then there is either inductive or capacitive or both reactance that kicks in, and so different things happen at that point. So special condition. So purely resistive, the value of the capacitor and the value of the inductor and that combination sets that resonant frequency, which is what we just showed and viewed. Now, what's at resonance? The current equals the voltage over Z, the impedance, and is maximum and in phase with applied voltage. The voltage of the inductor across the inductor or the capacitor can be much higher, and this goes back to that definition of resonance. The amplitude of the antenna at resonance is loud, and that's the thing that bugs the hell out of my family and fascinates me. But the amplitude is much higher. In an RF circuit, the voltage across the capacitor or the inductor or both can be much higher than the actual supply voltage, which is one of the things that they use in things like Tesla coils and all sorts of things. But it's also buck boost converters. DC to DC converters is what they use to boost that voltage up, and then they smooth it, rectify it, etc. So that's one of the special conditions. The voltage across those reactive components can actually be a lot higher at resonance, and that's based on obviously the Q, or the quality of the circuit, and Q is the ratio between the resonant frequency and the bandwidth, and that's very that's a condition, a characteristic, if you like, that's used through things like receiver front ends, where you actually want a number of different stages to give you that selectivity. What can actually happen is you get finer and finer bandwidth as you go through each of those selective stages, so that you end up receiving only the frequency that you want to receive. At a frequency below resonance, current's low, impedance is high, but we have a negative phase angle, which means it looks like it's capacitive in nature. There is capacitive reactivity, and at frequencies above resonance is the reverse to that. So there is a positive phase angle. So it looks like it's got inductive reactance. So there are different conditions that occur in and around resonance, which are very relevant to RF electronics and RF engineering. So, don't know whether you want to chip in there, Rex, or give us an example of resonance that you've played with, or something like that. So put you on the spot here.
You can. I guess you're going to talk next week about crystals that resonate, and basically a crystal is a quartz crystal which oscillates in the same way as your antenna does.
Well and truly.
Physically actually moves at a particular frequency, and they can move at frequencies up to over 100 megahertz.
Way over that.
And they have very high Qs. So
very, very high. I'm just looking in here because there is a wonderful picture of a crystal oh, there we go, crystal oscillators, and it's how they're actually cut in the crystal. So the reason why crystals are so high Q is they have a very incredibly well defined structure. This is atomic structure, so this is at the atomic level, and what you can do is there is a piezoelectric effect where if you put the crystal in between two plates and then provide some energy across those plates, you can actually get the crystal structure to start to resonate at a particular frequency that it's actually designed for. So absolutely fascinating, and this is in a fortnight's time, so I'm preempting it here, but we go into there are different ways to cut crystals for different applications. This is a quartz crystal, and I'm actually going to bring in some beautiful examples of large quartz crystals that are in my geology collection. So I'm using some geology and crystal X-ray. X-ray crystallography was a subject at university that I absolutely loved, for a whole range of reasons, and we might go into that a little bit. But different crystals resonate at different frequencies, and so and it up until quite recently, crystals in radio, and they still are used in radio to set frequencies. They still are used to provide a reasonably stable frequency, and then we apply things like GPS disciplined oscillators, so the GPS signal then disciplines that frequency and gives us really, really high stability. So yeah. So that's in a fortnight's time. Now we have a box out in the club rooms, which we've taken the covers off, which I'm going to show you some pictures of. The box looks a bit like this. Now what we're looking at here is a New Zealand-made Blyth 1 kilowatt AM broadcast transmitter. It is constant. It is 100% duty cycle kilowatt transmitter. So it's reasonably well made. And this is the front. This is the RF decks. This is the frequency, frequency generation, the amplifier, and then there is the control deck up here, and then there is the power supply down here. That is the toroid. That's the power supply deck. That's a toroid 2 kilowatt toroid power transformer at 125 and 180 volts. There is some filtering, some input and output frequency filtering, low pass filters and bits and pieces. That's the control deck up here. All of the electronics. Oh, that's the nameplate. Oh, that's a flower. I'm glad that's a flower. This is the power amplifier. So I think these three heat sinks, which run the length of the unit, and literally the fans are at the other end of the unit here, these three have a whole lot of what I suspect are MOSFETs connected to these heat sinks. So what we're looking at here, I think, is about 300 or 350 watts a heat sink here. There are many devices connected to those heat sinks. I'm not sure. Oh, there's another little low pass filter in there, I think, or a high pass filter, and that's the front. Oh, that's single malt Scotch whisky.
Just looking at the heat sinks, they don't look dramatically large for a AM transmitter, and I wonder if this is actually a Class D.
It could quite well be.
Yeah.
It could very well be. Until we get a, we have got service manuals on their way.
Yeah.
So until we get a service manual where we actually are looking at a, and that would actually, if they are MOSFETs, switching MOSFETs.
Yes.
That
might add up.
Correct. That might add up. So.
D or E.
Yeah. So it might be relatively efficient amplifier, although the power supply is 2 kilowatts. That transformer is rated at 2 kilowatts. So yeah. But anyway, that's sitting out there. We are probably considering whether we can use it on 160 meters. Up here, probably not at a kilowatt. I just say that out loud because we are not allowed to do that unless we have a high power license, which we don't. So the 400 watts is looking really good with a bit of headroom. So yeah, that's what's sitting out there waiting for us to work out what to do with, along with the audio processor that goes with it. That the audio processor was supplied with it. That's the thing that does all of the compression and pre-emphasis and etc. for the incoming audio, and then make sure that the transmitter's operating within its specifications. So yeah, that's a very interesting little box. So that's a bit of an intrigue that's sitting out on our desk and needs 2 people to lift it. Now, our antennas are here. Our 3.4 gig antennas are here. Our grid pack antennas. So I look forward to a little bit more testing around Hobart. The testing we've done thus far is very promising. Very promising. So we're getting the sort of coverage almost to getting the sort of coverage for 23 centimetres. So certainly Mount Wellington is an option, and certainly Mount Rumney is an option. They're the two that we've sort of all pointed at and been able to communicate with each other, full quietening on FM. So that's pretty promising. And once we get everyone up to the bigger grid packs, so the 27 dBi grid packs, I think we're doing pretty well. And those grid packs have also arrived in Launceston as well. So hopefully we can get some 3.4 gig from one end of Tasmania to the other. So that'll be good. Now, next week is our presentation night, and our presentation night on the 3rd of November from 7:30 p.m. is Scott VK7HSE, who is giving us a presentation on Digital Voice Hotspots. So these are the little devices that sit on your network. They also have a little very low power, in most cases 70 centimeter transmitters on them. They're usually like Raspberry Pi based, and it enables you to use your digital voice handheld in and around your house to get to all of those digital voice talk groups that you want to talk to, just literally by having a little Raspberry Pi sitting there with a little antenna somewhere in your house. So and uses the internet as the backbone. So even if you can't get to a repeater, can't see a repeater or get to a repeater, you can use these as your own little personal repeater, digital voice repeater. So that's Scott VK7HSE next week. So come along into our COVID-safe club rooms. Yeah, so we've got a whole lot of videos for our RF viewers. Oh, hang on. Richard, for those that can't see Mount Rumney, they will be dropped off tomorrow. Oh, excellent. Thank you, Richard. Thank you. Love your work. Love your work. I look forward to testing them on Sunday. So good stuff. So lots of interesting videos for our RF viewers. So that's our show for tonight. Thank you very much, Rex, and I look forward to the next instalment of WSJT development. So good stuff. All right, this is VK7OTC, the club station of the Radio and Electronics Association of Southern Tasmania, with our DATV Experimenters Night 73, and we'll see you in a fortnight's time. Cheers.